Okay. Any questions before we begin this lesson? I know there were a few from the worksheet over the weekend, so. Nobody has any questions from the worksheets? Okay. Well, I guess the only one was 5.4 that we added to that, so it shouldn't be too much. Okay. Let me just see where this is. Let me check messages. Where do we hand in the assignment? So you hand in the assignment in your OneNote page, just like you did with all the other stuff. So just create a new page in the quizzes tab and then just call it circular assignment answers, or just call it circular answers, I guess would be better. Keep it short. So today we're going to do the last lesson. The assignment's due Monday, or I guess today at midnight. Tuesday will be lesson 1, which is electrostatics, and then I'm posting the circular test on Wednesday. Okay, that works. I didn't realize that Monday, this like next week and 1 week from now, is a holiday, so we don't actually have class. So we really only have next Tuesday and Wednesday, because Thursday is kind of like the last assessment day, and then Friday's a day off. So I don't even think we're gonna start electromagnetism because it's just not enough time and it's not worth starting. So that's the plan for now. Okay, so energy with satellites. This is a kind of a new, yeah, you're gonna have to wrap your head around this a little bit. So let's talk about what we do know about potential energy already. Okay, we know that EP is mgh. Okay, and then based off of, if you like, here's the ground. Okay, and if an object is above the ground, then it has EP would be mgh, and this is the height above the ground. Okay, and we'll get back to that in a second. Now, we know that G is not always 9.8. Okay, it can change depending on where you are. So G is not constant, but rather depends on the radius or orbital radius, how far you are from the center of the Earth, and the mass of the Earth, or mass of, let's call it planet. Okay, so if G is gm over r squared and EP is mgh, then EP, put those two together, so m times g, gm, and remember this is the mass of the, so this is the mass of the planet, and this is the mass of the object. Okay, when you do mgh, like up here, that mass is the mass of the object, the thing that is above the Earth. So this is m object, m planet. Okay, and then over r squared, and then times h. Now, kind of a tricky part here. Remember that h is relative. Okay, you can change where the h is relating to. So like if I have an object on a table, I could say it has no potential energy because it's not going to fall off the table, but in reality it could. because it could fall to the ground. So really the ground should be my relative point because that's where EP is 0. So there's two ways we can look at this. We can say on the planet, if an object is on the planet, its EP is 0. Okay, because it's not going to fall anymore. And then like the reason we have potential energy is because something has the potential to fall towards the Earth. So we have on the Earth, it's not going to fall, so potential energy is 0. But there's also another place where it's also going to be 0. Okay, and that's out here where it's outside of the field of gravity. Okay, so remember the fire. If you build a fire, there's a point at which you will no longer feel the heat of that fire. Okay, it's like its radius of the field, I guess, radius of heat. Okay, at that point where you can no longer feel the fire, the heat from the fire, you're no longer in the area of influence. Okay, and that's the same thing with gravity. Okay, so if you are outside where G is 0, then EP is going to equal 0. Okay, so what I'm trying to say is this height here is relative to a certain point. Okay, and it's the same thing as the radius. Okay, so the distance, like you can say the height is the distance you are away from that point. Well, the R is also the distance you are away from a point. So the formula, if you look on your formula sheet, is, so this R squared will cancel out with that H, is G M1 M2 over R, but it has a negative sign in front of it. Okay, so let's discuss why that is. Okay, so when we talk about gravitational potential energy, we have to use a reference point. At this reference point, we assign the gravitational potential energy of 0. Okay, which is what's on the Earth, on the ground on the Earth, it's 0. When determining the potential energy on a mass provided by the gravitational force generated by a second mass, we assign the 0 reference point when the distance between the objects is infinite. Okay, or where G is 0. Okay, so instead of making this our reference point, the ground, we're making this the reference point. Okay, where it's escaped Earth's gravity. So instead of looking at potential energy as, so we used to think of it as, okay, here's an object above the Earth. How much energy does it have when it will fall towards the Earth? Now we're going to flip it and say how much energy is required in order to escape Earth's gravity. Okay, that's the EP we're talking about now. It's how much energy is required to escape Earth's gravity. Okay, and that's how we're going to relate potential energy. So whenever the object gets closer together, the potential energy between them gets less compared to infinity. The potential energy is, so if this is EP and this is R, okay, if you think about it being negative, if the R is really, really small, because it's a denominator, the value of EP is going to be really, really big. But because it's really, really big negative, it's going to be down here somewhere. And then as the R approaches infinity, or gets much bigger and bigger and bigger, as you get further and further away from the Earth, the EP eventually becomes 0. Okay, and so your graph kind of looks like this. Okay, as it approaches 0. Okay, hopefully that sort of makes sense. So the big key here is, instead of saying how much energy will the object have when it falls towards the Earth, it's how much energy is required to escape Earth's gravity. Okay, that's the big thing that we're talking about here. So, example, 2,500 kilogram satellite is in orbit above the Earth's surface. So this is altitude, because it's saying above the Earth's surface. It's not orbital radius. What is the gravitational potential energy of the satellite due to the gravitational force due to the Earth. Okay, so let's plug this into our new formula. EP equals negative G M1 M2 over R. The R, actually, I'll just do it here. Negative 6.67 times 10 to the negative 11 times 2,500. It doesn't matter which mass is which, whether it's M1 or M2, as long as you have the mass of the satellite and the mass of the Earth. 5.98 times 10 to the 24. And then over R, R is going to be 3.6 times 10 to the 7 plus 6.38 times 10 to the 6. Okay, that's the new radius. And that will give us a value of 10 to the negative 11 times 2,500 equals divided by that's right. Okay, so then this is negative 2.35 times 10 to the 10 joules. I hope I did that right. I just need to double check it because I think I typed something in wrong in my calculator. Yeah, that's right. Okay, so what this means, where did I get 6.38? This is the radius of the Earth. I think. Pretty sure. I hope that's not wrong. Right, because it's above the Earth's surface, so this is the Earth and this is the satellite. This distance is 3.6 times 10 to the 7. But because it's orbital radius, we're always referring between the centers of the object. You have to figure out this total distance right here. So this right here is 6.38 times 10 to the 6. The radius of the Earth. Okay, so what this means is if I wanted this, because this satellite right now is, if this is the Earth, this is the satellite right here. Right here has a potential energy of negative 2.35 times 10 to the 10. Okay. Over here, where G equals 0, EP is 0. Okay, and keep in mind that G will equal 0 at infinity, right? If you look at the formula for G, that only happens when radius is really, really, really high. Okay, it actually can't equal 0 because G is not going to equal 0, M is not going to equal 0, and R can't equal 0, which is why this always approaches 0. Okay, so this occurs at an infinite distance. Now, like, it's not infinity. That's not, like, obviously, it doesn't take very long to escape Earth's gravity. Just like a fire, technically, you can't be infinite distance away from it, but you're not going to feel its heat because it's going to be so little. Okay, the value of G is we approximate 0. Okay, so what that means is from this point to this point, I would have to give the satellite 2.35 times 10 to the 10 joules in order to escape Earth's gravity. So I would have to input this much energy to escape G. Okay, so that's what this blurb is here. The potential energy of the satellite relative to some infinite position is the amount of energy required to get to that point. Infinity away. Okay, and like, infinity isn't a number. I'm just saying really, really, really far away. Okay, it's not we're just approximating a distance. We're not saying it's a certain distance. So yeah. Okay. What is the total amount of energy in that of the satellite in that last question? Okay, so we found the potential energy of the satellite, but it also has kinetic energy. Okay. And it has kinetic energy based off of its velocity. So we would need to find its velocity at that point. So in order to do that, we could say AC equals G. So V squared over R equals G M over R squared. And we're solving for R again. So this is going to be the same formula we had last time. V equals the square root of G M over R. Okay. So then the EK would be 1/2 times M times V squared. Okay. And so then if you plug in the velocity into that equation, you get EK equals 1/2 times M. And if you square a square root, you get rid of it. So this is going to be GM over R. Okay. And so this is going to be 1/2 times, now we need to look at the masses. So this is the mass of the planet. This is the mass of the satellite. Okay, so the mass of the satellite was 2,500 times 6.67 times 10 to the negative 11 times the mass of the planet, 5.98 times 10 to the 24. And then divided by the radius. The radius again is 6.3. No, 3.6. I'll just do this one first. 6.38 times 10 to the 6 plus 3.6 times 10 to the 7. That's our orbital radius. Okay. And so we can find our kinetic energy, 6.67 times 10 to the negative 11 times 2,500 times 5.98 times 10 to the 24. Then divide by 6.38 times 10 to the 6 plus 3.6 times 10 to the 7. Okay, so this EK is 1.176 times 10 to the 10 joules. Okay, and then the total energy, ET, will equal the EK plus the EP. Okay, so this is going to be 1.176 times 10 to the 10 plus negative 2.35 times 10 to the 10. And so that's going to be minus 2.35 times 10 to the 10. And this hopefully freaks you out a little bit. Negative 1.17 times 10 to the 10 joules. Okay. Hopefully you're noticing something right now. The total energy is equal to the negative kinetic energy and half of the potential energy. Now I've kind of already derived this. So the actual relationship is ET is equal to 1/2 of EP. Okay, and I'll show you why. Okay, so I'm going to take this right here, EK equals, and I'm going to rearrange it, 1/2 times G times M satellite times M planet over R. Well, this right here is EP. So remember that EP is negative G M1 M2 over R. And so this is the same thing, but negative. So we can replace that with EK equals 1/2 times negative EP. Okay. And the total energy will equal the potential energy plus the kinetic energy. So now we have potential energy plus 1/2 of negative EP. Well, EP plus 1/2 negative EP is, so the total energy will be 1/2 EP because it's 1 EP minus 1/2 EP. And that is the trick for satellites to find their total energy. Okay, all you have to do is find the potential energy and then apply and just do half of that and you get the total energy. So kind of cool. Okay. Changes in potential energy. Now, when you, so this is kind of the same thing as like if we have an object right here and we, let's say we right here is its initial position and then right here is its final position, okay? We're doing work against gravity and this would be a delta EP, okay? Work against gravity. Well, satellites is the same thing, okay? If you want to change their orbit, so how far it is away from, I guess in this case, how far it is away from infinity, then you're doing work against gravity. So it's a delta EP. Okay, so the amount of work to change your potential energy or position is a delta EP. So there's a quick little formula we can use. If we look at delta EP as final minus initial, if I'm going based off of final, so EP final is negative G M1 M2 over RF minus initial negative G M1 M2 over RI. What happens is this becomes positive. And so if I write it first, I get delta EP equals GM1 M2 over RI minus GM1 M2 over RF. Okay, so now it becomes like, so the initial became positive because the individual potential energies are already negative. Okay, so I'm just flipping this. So this one comes first, this one comes second. And then if you factor this out, you get delta EP equals G M1 M2 1 over RI minus 1 over RF. Okay, and that's the quick little formula to find your delta EP for satellites. Okay, it does the negative for you. Okay, so the negatives are already built into this formula. We're just deriving how to get a short version of it. Okay, and you don't have to. You can just do this over and over again and you'll get the exact same answer. Okay. The only reason this is nice is because it makes it a little easier to put into your calculator. So how much work is required to move a 4,500 kilogram Earth satellite from an orbital radius of 1.8 times 10 to the 7 to a radius of 4.2 times 10 to the 7. So it's getting further away from the Earth. Now, if you're going further away from the Earth, you're doing work against gravity. So I would expect this work to be positive because it's an input of energy. Okay, and so let's figure out if that's true. So the work we're doing is a delta EP, and the delta EP is going to be that formula right there. So 6.67 times 10 to the negative 11 times 4,500 times 5.98 times 10 to the 24. I'm going to run out of room. 1 over RI, so 1 over 1.8 times 10 to the 7 minus 1 over RF, 4.2 times 10 to the 7. And then I can calculate that. So quick way to do the 1.8 times 10 to the 7 is using an inverse. So 1.8 times 10 to the 7. I don't know where my inverse button is. There it is. And then minus 4.2 times 10 to the 7 inverse. And then multiply that by everything else. 5.98 times 10 to the 24 times 4,500 times 6.67 times 10 to the negative 11. And this is 5.7 times 10 to the 10 joules. Okay, and it does come out as positive because it's an input of energy. Okay. Okay, now, any questions about that? Any questions about anything I've done so far? Okay, so when you're changing radius, the only thing that matters is the change in potential energy because the work is done against gravity. Okay, now remember that if we have an object in the air, okay, this is the initial position and this is the final position, so we're dropping it, okay, because things drop to the earth. They don't, like, unless they're in circular motion, but we can, like, the next example of the space station drops a 250 kilogram waste shuttle. So that means it's going to shoot it down towards the earth, not in circular motion. So it's going to fall towards the earth. So remember that initially this had EP and the EP here is 0. And the EK here is 0. And the EK here is whatever it is. So we said in conservation of energy, the EPI will equal the EKF. Okay. In reality, it's actually EPI plus EKI equals EPF plus EKF. Okay. And so if you rearrange this to get, let's go, we'll move that to that side and that to that side. So you get EKI minus EKF equals EPF minus EPI. Okay. EKI minus EKF is the exact opposite of delta EK. So we can go negative delta EK equals delta EP. Okay. Or delta EP equals negative delta EK. Doesn't matter which one gets that. So what this is saying is that the change in potential energy when something moves up or down is equal to the negative change in kinetic energy. Okay, now this formula is very, very, very important for the next 3 units. Now we're only going to do next 1 unit. Well, this unit and the next 2, so that's why I'm saying 3. But it's important because if we look at something like this, where the International Space Station drops something, so here's the Earth, here's the thing that's dropping, the change in potential energy it has, because it's going to go from here to there, is going to equal the negative delta EK. Okay? And so, and remember that EK equals 0 in this case. Okay? Now, a satellite, the EK isn't 0, but we assume it is. Like this space station is dropping the 250 kilogram waste. Okay, so even though it's traveling in a circular motion, in order to drop, you have to stop it moving in a circular motion. Okay, because if it doesn't stop moving in a circular motion, it's just going to stay in circular motion. Okay, that's the whole reason we have satellites. Okay, if the moon stopped moving, oops. So here's the Earth, here's the moon. If the moon stopped moving that way, it would fall. Okay, the reason it keeps moving is because it's in circular motion. So if you stop it moving in circular motion, it starts to fall because gravity is still there. So we're stopping it moving in circular motion, which means that we're stopping it. So its kinetic energy becomes 0. Okay, so in this case, what speed would it impact the Earth? Okay, if there's no air friction. So we can say delta EP equals delta EK. Now, delta EP, it doesn't end at 0. Okay, the potential energy is not 0 when it hits the Earth, because we're switching the relative point. Okay, relative point is no longer the surface of the Earth; it's some point way out there. So the way this formula works is G M1 M2 1 over Ri minus 1 over Rf will equal negative, so this is negative EKF minus EKI. Okay, now this EKI is 0 because it's starting, EK is 0 at this point because we're stopping it. And so we get negative 1/2 mv squared. Now remember that the mass like this mass is the mass of the actual waste shuttle thing. Okay, so we can cancel it out on both sides. And so we're left with 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24. And then 1 over Ri. Ri is, oh crap, okay. So Ri is going to be, because it's altitude, so it's 3.5 times 10 to the 5 plus 6.38 times 10 to the 6. So that's 6.73 times 10 to the 6. And then minus R 1 over RF. RF is 6.38 times 10 to the 6 because it's ending on Earth equals negative 1/2 v squared. Okay, so let's do that first. 6.73 times 10 to the 6 inverse minus 6.38 times 10 to the 6 inverse times 5.98 times 10 to the 24 times 6.67 times 10 to the negative 11 equals, and then so this side of the equation becomes negative, and I'll just write all the answers, 3 to all the numbers, 51317.034, that's what I get in my calculator, equals negative 1/2 v squared. Now it's good that it comes out as negative, okay? So remember that it's not working against gravity, it's working with gravity. It's going in the same direction as gravity, therefore the work is negative. You don't have to put in energy to make it fall. You just have to stop it and then it'll fall because gravity will pull it. So that means like both sides are negative, which is a good thing. Okay, so that we can cancel it out. So times by -2 and then square root, answer. So this gets us a velocity of 2,550 meters per second. Okay. So if that doesn't come out as negative, you know you did something wrong because you're going to have to cancel the negative in order to square root. Okay, any questions about that one? I think there's another example. There is another example. Okay, let's do another example. So, oh, here we go. This is just a question mark. Okay, try. Oh, there it is. Oh. Oh, crap. I joined the meeting on my phone. That was a bad idea. Okay, let me just check this. Okay, but both has to be negative or only right side. No, so the work, the change in potential energy has to come out as negative because the kinetic energy is already starting as negative, right? It gets the negative from here. So both sides have to be negative in order to square root it because you can't square root a negative number. That's what I'm trying to say. Okay. This next example is very similar, so let's just look into this, and then if we still have questions, we can ask. So really big asteroid falls towards the Earth from a really far away. How much energy is released when it impacts the Earth? So how much energy impacts the Earth? So this is EP plus EK. No, that's not right. I think it's just EK. Let's find EK and then we'll decide. Okay, so if you think about this, here's the Earth, here's the satellite. Hang on. Oh, no question. It's weird. If it's really far away, the initial potential energy is 0. And the initial kinetic energy is also 0. Okay. So in terms of our formula, delta EP equals negative delta EK. It's EPF minus EPI equals negative EKF minus EKI Okay, the EPI is 0 and the EKI is 0. So then you get EPF equals negative EKF. And so I think I'm doing this right. The amount of energy, well, we can solve for, I don't know what we're solving for here. We don't have that right in radius. Okay, let me just keep going here. Okay, so what I'm trying to say here is, like, because it's really, really far away, the potential energy is 0 because we're assuming that G is pretty much 0. Okay, and if G is 0, it's not going to fall towards the Earth. So it's really, really far away, so it's starting at 0, and then it's moving towards the Earth, so eventually it's going to get into our Earth's gravity and then start moving towards it, okay? So if you go based off of this, EPF is going to be G M1 M2 over R negative equals negative, and then 1/2. Oh no, I don't want to find that. Let's just find EKF. Okay, because that's going to be the energy that it impacts with. And so negatives will cancel out, and we're left with 6.67 times 10 to the negative 11 times 2.35 times 10 to the 16 times 5.98 times 10 to the 24 over the radius of the Earth, because it's ending on the Earth, 6.38 times 10 to the 6. Okay, so the potential energy doesn't, like, when we're asking how much energy is released when it impacts the Earth, if you think about it this way, if something impacts the Earth by falling towards it, the potential energy at this point is 0. Okay, so it's not going to impact the amount of energy there is at this point. So it's only the kinetic energy that's going to be released. Okay, and the same thing is true for this case, even if we flip it. The potential energy at this point has nothing to do with released energy. All it means is that much energy is required to move back to that point. Okay, so it's not actually released. So the actual energy that's released is the kinetic energy, and that's what we're trying to find right now, EKF. Okay, so this, all these numbers here is this formula right here, GM1 M2 over R. Okay, negatives cancel out, and I'm finding EKF. So in this case, it would be 6.67 times 10 to the negative 11 times, that's a large asteroid, times 5.98 times 10 to the 24, divided by 6.38 times 10 to the 6. And the answer is, so EKF will be 1.5 times 10 to the 24 joules. Okay, so that's a lot of energy. Okay, any questions about that? It's the exact same thing as conservation of energy. Okay, and if you stick with this formula right here, you can do that every time. Okay, because that is conservation of energy. Okay, last thing. And remember that tomorrow is not, why is the EPI 0? EPI is 0 because G is 0. Okay, because when it's really, really, really far away, it's not in the Earth's gravity. And if something isn't in the Earth's gravity, it's not going to have potential energy. Like, this is still true, EP equals mgh. That's still true. Okay, but if G is 0, then EP will equal 0. So if something's really, really far away, G will be 0 because it's not in the Earth's field, the gravitational field. Then the potential energy would be 0. That's why the EPI is 0. Okay. So the delta EPI would be 0. Not the delta means change in. So you can't have a change in the initial. Change is always final minus initial. which is why, so I'm doing final minus initial rate here, which is why I just end up with EPF, because EPI is 0. And the same reason here, EKI is 0 because it's just falling from some point. And so this side of the equation becomes negative EKF. Does that make sense? Okay. Kind of. So no. I hate this lesson. Okay. Let's just finish this and then you guys can ask questions again. So launching escape velocity. So if you want to, like, so what I'm saying is, like, the whole thing about this, like, if you want a satellite or any object that's on the Earth to escape the Earth's gravity, so remember that the Earth has a gravitational field around it where anything in that field is going to move towards the Earth, okay? If we want something to go beyond that point where it's no longer going to fall towards the Earth because G is 0, we need to give it enough energy to reach that point, okay, to escape the Earth's gravity, okay? And it, like, think about it this way. If you throw something in the air, it's going to fall back towards the Earth, okay? Because gravity, things fall down. But if you throw it really, 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 really hard to a point where G is no longer 0, outside of the Earth's gravitational field, it's not going to fall back, okay? Because you threw it hard enough. It escaped Earth's velocity, or Earth's gravity. Okay, this is called escape velocity. So this is the minimum speed an object requires in order to break free from the Earth's pull and achieve orbit. And that's not technically right because orbit requires gravity. So let's not get to that point. Like, we're talking beyond the moon. Okay, the moon is still affected by the Earth's gravity. It's not very big, but it's still there. So we need to, okay, so it should stand to reason that if an object is going to completely freed from the Earth's gravitational pull, we need to supply it with enough kinetic energy to match its total energy. I don't remember what that is, at infinite. Okay, so in terms of what that means, so let's look at it this way. I already have this done here. So we have EPI, okay, and remember that EPI is the amount of energy it has that we need to give it to escape the Earth's gravity. EPF will be 0. Why? Because it's outside of the Earth's gravity. It's no longer going to fall towards the Earth, therefore it has 0 potential energy. Okay. Now, if we, in order to get it to that point, we need to give it enough kinetic energy. And when it reaches this point, because we're giving it a minimum amount of energy, okay, which means that it's going to stop at that point. So remember, if you have an object and you throw it up, eventually it's going to stop and then fall back. We want it to stop where G is 0. Okay, so that's the minimum amount of energy we need, where it stops when it's 0. If it stops anywhere before that, it's going to fall back towards the Earth. Okay, so we want it to stop when the kinetic energy is 0. Okay, so notice how there is no energy at the end. So that must be whatever. Don't worry about those blanks. Those don't make sense. Okay, so in terms of equations, if we look at this equation again, delta EP equals negative delta EK. Okay, we've delta EP, so EPF minus EPI equals negative EKF minus EKI. Now our EKF is 0 and our EPF is 0. So now we have negative EPI equals EKI. Okay, and we want to know how much energy is required, or what the minimum speed is required to get it out of Earth's gravity. Okay, so if we look at this, negative EPI is going to look like this. Negative, so let me do it up here. Erase. Negative EPI equals EKI. Does everyone understand that equation? How I get that? Okay, and it's super helpful to draw pictures like this. Okay, so we're trying to get it from the surface of the Earth, where the potential energy is relative to the point where it's 0. Okay, and we're trying to escape Earth's gravity. That's why our final kinetic and potential energy are 0. Okay, so this will become negative G M1 M2 over R. Okay, that's Ri equals 1/2 times mv squared. Now the mass of the object will cancel out. This is still the mass of the planet. Okay, remember that the object that has kinetic energy, that's the mass. Okay, the mass that's in that formula is the object that has kinetic energy. So this becomes G mp over R equals 1/2 v squared. Oops, squared. And so if you solve this, we get v equals the square root of 2gm over r. Now notice how the mass of the object cancels out. The mass of the object does not matter. The only thing that matters is the speed. Okay, it's whether you throw a 1 kilogram rock or a 1,000 kilogram satellite, it's going to be the exact same speed you need to give it in order to get rid of it, to move it away. Okay, now it'll be a different amount of kinetic energy because it's dependent on mass and velocity, but the speed at which it leaves is independent of mass. Okay, and so we can find this pretty easily. 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by, looks like 11, 6.38 times 10 to the 6. So 2 times 6.67 times 10 to the negative 11 times 5.98 times 10 to the 24 divided by 6.38 times 10 to the 6, square root that, and you get V is 11,182 meters per second. Okay, and that'll always be the answer. Okay, what is the minimum velocity required to escape the Earth's gravity? 11,800 or 11,182 meters per second, regardless of the object. Okay, so does the mass of the rock matter? No. The only thing that matters is the speed. Okay, any questions? Whew. That was a tough one. Okay, so now you can do the rest of the other worksheet and the, what was I going to say? Let me stop sharing for a second. Okay, you can do the rest of the worksheet and you can finish the assignment. And then that's it for today, I think. I won't be very available for the rest of the day today because I'm taking my family camping, and then I'll be back tonight for tomorrow. So I'll try to answer questions this afternoon, but I might not be able to, but I'll definitely answer a lot of questions tomorrow. I'm not in any rush to start electrostatics at all, so tomorrow might just be like a pretty heavy review day. And that's probably it. So yeah, just create a OneNote page or add another page to the quizzes tab and then call it circular answers, and then that's where your worksheet answers go. And then I think that's it. So I will talk to you guys tomorrow if there's no other questions.
I have a question for also our worksheet.
Yeah.
I have a question for a 5.3 A question.
Okay. Oops. Okay, 5.3. Number 8?
Yeah, number 8.
Okay. Let me get rid of this. Okay. 3 10-kilogram objects are placed in a straight line, and they are 0.5, so like 50 centimeters apart. What is the net gravitational force on the center object? Okay, so if you have 3 objects, 1, 2, 3, and they are equal mass, 10, 10, 10, and you want to know the force on the center object, well, this one is pulling the center object that way. This one is pulling the center object that way. And the FG is going to be Gm1 m2 over r squared for both of them. Well, because it's 10, 10, and then the same radius, this force of gravity will equal this force of gravity, making the net force of gravity 0. Because they're the exact same mass, exact same distance. Now, if one of these, like this was 20, well, then the net force would be in the right direction, and this one would move to the right. Okay, but because they're all the same mass and same distance, it's the same amount of force going in both directions. That's why it's 0.
Okay. Yeah. Thank you. And then can you go over worksheet 5.4 number 1 question?
Number 1. Okay. Okay, so calculate the gravitational field strength on the surface of Mars. So that means there's Mars, there's the surface. Okay. Now the value of G is going to be Gm over r squared. And so it's just going to be 6.67 times 10 to the negative 11, that's universal, times the mass of Mars, which is 6.37 times 10 to the 23. It's 23. And then divided by the radius of Mars, 3.43 times 10 to the 6. And then whatever that answer is. This is going to be 3.61 meters per second squared. Okay, and that's it. And like it's asking for the surface of Mars. So that means the distance is from the center to the outside, which is the radius. That's why I'm doing 3.43 times 10 to the 6.
Thank you.
Yeah. Okay. Any other questions? Okay. Well, I guess that's it for today, and I will see you guys tomorrow, and we'll go over more questions tomorrow. So have a good rest of the day.